Warm welcome from IIT Kharagpur, and thanks to all of you for choosing the course, the NPTEL online certification course on soft nanotechnology. You will soon realize that this is a course which is pretty advanced, and it's at the interface of soft condensed matter physics, a lot to do with polymeric materials, nanotechnology, bit of physical chemistry, and surface physics as well. It also has a lot of engineering applications, and we find a whole lot of applications in chemical, mechanical, and other conventional engineerings. So this is the team. I'll be your instructor, and you can sort of go to my home page. The home address is a bit complicated, so I suggest you search in the Google, and the first search Google with my name, and the first search result will take you to my home page. I encourage you to use the online forum that will be offered during the course for your questions and queries, but in any case you can always get back to me or send me an email. But I will definitely redirect it to the online blog or discussion forum, because I want any doubt that is particular to any one of you should be known to all the participants. This course I will be assisted by two of my very bright students. Both are outstanding scientists in their own credit, Dr. Nandini Bhandaru and Ms. Anuja Das. Course content, well, it's a bit out of box course, so we will have a bit longish introduction on, and the themes we will cover. Many of you know what is nanotechnology, what is so unique about it. Specific coverage of this course, so we will talk about nanopatterned surfaces and stability of ultra thin films. In fact, these are the two major areas which we will focus, which are also very important from the standpoint of nanotechnology, but often overlooked. I mean, people are more worried about quantum dots and things like that, finite size effect, but these are equally important issues where the effect of nano or the mesoscale are prominent. Then we will talk about some of these so-called nanopattern surfaces and talk about the associated science with it. In order to progress, then we need to clarify some of the basic concepts like surface and interfacial energies, components of them. The wetting regimes, that's a very important concept. We will talk about the Young's equation, which talks about the balance of surface energy when you put a drop of liquid on a solid surface. Then we will talk about wetting on a nanopatterned surface, which is very important. It gives rise to the hydrophobicity, the Cassie and Wenzel state, and is responsible for, let's say, rolling of a water drop on a surface of a lotus leaf. And that will also give us the platform to talk a bit about Laplace pressure. That's an immediate effect of surface tension, and essentially the Young-Laplace equation. So for the first time, probably for some of you, we will come to know that a liquid surface in mechanical equilibrium may not have the identical pressure on both sides if it has curvature, and this pressure difference is entirely attributed to surface tension. Moving on, we will talk about patterning techniques. As I told, this nanopatterning is one of the key focuses of this particular course, and it is soft because we will be dealing mostly with soft materials, the materials that can be deformed by gentle forces. These forces can be externally applied mechanical forces, or a very, very important thing at the nanoscale, the van der Waals forces, and that's why we have specifically chosen this soft materials or polymers. But it is not limited to polymers. You can even process inorganic materials through the soft route, or you can also have gels and things like that. But anyway, talking about the patterning techniques, we will talk about the nanofabrication methodologies, the so-called top-down, bottom-up, self-assembly, and I'll also give you a quick introduction to surfactants, which is a very, very fascinating set of molecules. We will then go on talking about brief introduction to photolithography. Now, photolithography itself can be a semester-long course, but I will just try to give you a basic essence of what is photolithography and what are the major components or major steps associated in photolithography. Then we will move on to very polymer-specific or soft material-specific soft lithography techniques, and here are some of the methods that we might be we will be talking about, like nano-imperial lithography, then capillary force lithography, micromolding in capillaries, microcontact printing, and I assure there will be some more to come. Then we will talk about, so one of the key issues is that as you fabricate something that's in the nanoscale, you also need to visualize or see them. And one of the major tools that has in fact significantly enhanced research or contributed in the development of research in nanoscience area is the atomic force microscope. And we will talk a bit about the atomic force microscopy, basic principles, basic operating principles, including that of the STM, and we will talk about the different modes and the additional features of an AFM in a very condensed manner, but this will sort of give you an idea of what an atomic force microscope can do. This will be roughly at the middle of the course, midpoint of the course, and then we will shift gears a little bit, and we will move on to instability, the spontaneous instability and dewetting of thin films. Particularly, we will be talking about polymer films, which one needs to sort of take in the liquid form to see or observe these instabilities. We will talk about details when the context comes, and for that we need to have a good understanding of van der Waals interaction between two surfaces. That's an important area. Spreading coefficient, we will have to talk or learn what is disjoining and conjoining pressure. Origin of spontaneous instability in an ultra thin film, it's essentially a competition between Laplace pressure, which I already told it has its origin in surface tension, and this so called disjoining pressure. Then we will talk briefly, rather qualitatively, this one can look mathematically also, but we will make it look qualitatively in hydrodynamics of a free surface, free liquid surface, morphological evolution, dewetting of a thin film. We will then talk about more complex situations like dewetting and instability of a thin bilayer, dewetting on a patterned surface. I'll also try to give you a bit of introduction on phase segregation and demixing in a polymer blend film as you spin coat. This is a very interesting area, and maybe I'll restrict it to just one lecture or something like that. Finally, I will give you an introduction or give you an idea about elastic contact instability, another very fascinating set of instability observed in elastomeric polymers, rubbery films, and I'll give you glimpses of how this technique has recently been used for making nanostructures in a very controlled way. So the concepts of we'll talk about patterning beyond a negative replica, that's patterning beyond a master, a new concept that's coming in patterning, and as we make progress you will understand it in more detail, and then we will wrap it up nicely with conclusion and future prospects. So happy learning. I'm pretty sure that you are going to enjoy this course. This is a pretty open-ended course where developments are taking place even now. So most of the subjects or topics we are going to cover are sort of the research in this whole area started in early 90s. So you can now understand that this is indeed very recent as compared to, let's say, classical areas what you study in your textbook. For example, the apparently very novel concept of a boundary layer is about more than 100 years old. So these are new things. So the course is still evolving, the topic is still evolving. You find a whole lot of things coming up, whole lot of new findings coming up in top level journals even now. So I might take the liberty of sort of changing the topics a bit to make the course cohesive. What you need to understand is this is a very compressed course. I'll try to make it as lucid as possible so that you enjoy the essence of the subject and flavor. It is more of a non-numerical course, so don't expect assignments where you have a specific formula, you plug in some numbers, get a direct calculated value. It's not going to be like that. Even the assignments are they're going to be very easy, because I believe that it is important that you enjoy and learn something rather than digging your brain in doing something that is very difficult to do. So I would request all of you to follow the lectures, follow the text and the supplementary materials that I will supply, and please try to participate in all the assignments. I'm sure it's going to be very easy. So the resources for this course, one of the problems of something that is very recent is that you don't have a textbook. Textbooks will be too scattered and things are taken from here and there, so don't get in or search for a textbook. However, you can use NPTEL resources, because I have two courses. One is a web course where you get all the text, and there is also a set of video course which goes by the name Instability and Patterning of Thin Polymer Films. This is also an elective that I offer at IIT Kharagpur in the spring semester. So I would strongly recommend you to either note down these two URLs and use them. So here this is a web course, here this is a video course. You can also go to this NPTEL AC in website, go to chemical engineering and search with the name instability or search with my name, and I'm sure you will get them. In addition, this video course, the contents are available in the YouTube. So the best option is just search in YouTube with my name and you will get it. This is a 40-hour course, in fact, where things have been discussed in much greater details. So it will act as a very good guide for anything that you need to sort of consult. So particularly this web course which is written, so you can use it as sort of a text. What I will also do is all the PPTs that I am using and all the handwritten text that sort of analogous to the blackboard in this format of a course that we will generate in course of our discussion, I will upload them for your reference. So all these things will be at your disposal. So you are free to consult anything that you want to need at any point of time, and then just follow the norms of this NOC curriculum or courses. Resources, I will also, in addition to this NPTEL resources, there are quite a few book chapters or chapters mostly I have written. So these I will sort of upload for your perusal. So you can use any one of them, and as time comes I will just tell you which part of the course you need to consult which of the book chapters, but you can see it yourself, and this roughly covers almost everything, maybe other than the atomic force microscope. You will find everything is covered. Atomic force microscope, of course, is a pretty popular instrument, and a lot of resources are already available in the net. I would also strongly encourage you to consult Wikipedia. As a first learning step, Wiki is a great place to learn. So please feel free, find out the keywords. If you find anything that is new, just go and search in the Wikipedia. You will get some idea about it. So these are the things. Well, as I already told, that a lot of developments in this area are taking place even now, and any scientific discovery or advancement is reported in top scientific journals. So there are a whole lot of journals where one finds this type of papers coming out. I understand that availability or accessing journal papers might be difficult for many of you because you need access, and which we have in IIT. So even if you can't access, you can always see the abstract. You can search or find out these journal home pages and see what type of papers are coming out. So some of the top journals in the field, or even in the field of science, is Nature, Nature Materials, Science, and very specific to our topic would be a journal from American Chemical Society, Langmuir, Applied Physics Letters, Advanced Materials, Small Macromolecules, etc. You can find out the home pages and things like that. If a particular paper interests you, you can always mail to any one of us, and we can mail it back to you. So that is sort of what is the course content. So let's get started with a very short introduction. So what is the first thing that comes to your mind if we talk about nanotechnology? And the first thing that comes to your mind, of course, you all know that nano is 10 to the power minus 9 meter. Compare it with a human hair. I have a figure somewhere, picture somewhere down the slides, which is about 50 to 70 micron. So now you understand what we are talking about, how small we are really talking about. What is the rather established research area in nanotechnology is the so-called quantum confinement in nanostructures. So either you can have a sheet-like material where it's a 2D structure. In fact, the electrons are confined in one direction. You can have wares where the electrons are confined in two directions, or you can have dots or nanoparticles where the electrons are confined in all the three directions. So this, in fact, this so-called quantum dots are one of the basic fundamental building blocks of nanotechnology. They find that these are essentially made of same material as ordinary semiconductors, mainly combination of transition metal or metalloids. But unlike ordinary bulk semiconductors, which are generally macroscopic objects, quantum dots are extremely small, on the order of few nanometers, and they are therefore considered to be nearly zero dimensional. according to this set of definitions. So, this is a 0D object, the where is a 1D object, and a sheet is essentially considered to be a 2D object. And here, so it is 2D. So, from a 3D object you lose in one direction, so it is confined in one of the directions, therefore, it is 2D. Here it is confined in two directions, therefore, it is 1D, and so on. These are not very important from the standpoint of our course. I just want to show where our course, what you are going to learn, is different from the classical nanotechnology, what you would typically learn, which requires a lot of understanding on quantum mechanics and stuff like that. So, what does it lead to? What it leads to is, you know that every material has a specific band structure, and which is responsible for various properties of the material, including optical properties. So, let us say this why gold looks so beautiful is because it has certain specific surface plasmon resonance when visible light falls on gold. And what happens is, if you go on making things smaller and smaller, the band structure due to confinement gets changed. So, this is a very simplified, simplistic picture of this quantum confinement effect, and as a result what happens is the intensive properties becomes extensive. So, what exactly is intensive properties? Intensive property is properties that are independent of the size of a material. So, let us say whether you take 100 grams of gold or 1 gram of gold, it looks the same, but if you go on to smaller and smaller dimensions, there is a possibility that things might look completely different, and that is exactly what happens. So, for example, here any guess what it is? Well, it turns out to be gold nanoparticles. So, if you go down to synthesize gold nanoparticles which have size in the range of 10 nanometer or less, because of this confinement effect there is a change in the band structure, and you get completely different colors. So, if you look at this particular picture, this type of pictures are pretty popular for people doing research in quantum dots. These are essentially quantum dots of the same semiconducting crystalline material, but the sizes are different, and if you now illuminate them with, let us say, some light source like UV, they transmit different colors. So, this is unique because they are all made of the same material, but the only difference that is there is their sizes are different, and that is exactly, it endorses what I just told you, that intensive properties, for example, the appearance or the color of a material is its intensive property. It does not depend on its size, right? It does not depend on how much material you have taken, its properties starts to deviate. So, this is one of the aspects of nanotechnology, the so called quantum dots, quantum confinement, the finite size effect, you name it, and this has received significant amount of attention. However, this is not what we are going to talk in detail in this course. There are some other aspects of nanotechnology, or there are some other issues that are extremely important in the nanoscale, which are not that well emphasized in many of the settings, and that is something that we are going to talk about in greater detail. So, let us try to figure out one particular aspect. What are the dominant forces at the nanoscale? In a macroscopic world, we always see that everything is dominated by gravity, but as you go down in size, if you look into molecules, or if you sort of go down much in size, in fact you find that gravity almost becomes negligible. It is because of the fact that gravity, sort of the interaction forces, scales as mgh, h is sort of the height or the separation distance, you can say, and as this h becomes smaller and smaller, this gravitational force becomes tends to become negligible. So, what are the other forces? And the other force that really dominates at the nanoscale is what is known as the van der Waals forces. This is something we all know in somewhat detail, but I think for as a part of this particular course we will talk in some sort of a greater detail. This course, these forces, this so called van der Waals force we are talking about, is the induced dipole induced dipole interaction between molecules. This again has its origin in quantum mechanics, but we will take a very simplistic picture. Maybe we will lend some concept from your high school physics or chemistry. How does a molecule look like? So, you have a nucleus and which is surrounded by these electrons. So, this is more of a picture we are all pretty well conversant with. This is also what is called as a Rutherford atom, because Rutherford proposed this picture. In reality, of course, the structure, the situation is not so simple, it is slightly different in the sense that these electrons actually undergo a very high frequency oscillation around the nucleus. And as a result, at any given instance of time, there is in fact a localization of charge. So, this electron cloud, and please do not forget that this is not on one particular plane, this is in the whole 3D space surrounding the nucleus. The electrons are oscillating, they are rotating at a very high frequency. So, at any instance of time, what it means is that at any instance of time, the charge distribution within the electron cloud is non-uniform. And what does that lead to? In fact, that leads to some sort of a localization of a charge of delta minus over a particular location of that particular electron. Now, what does this temporary charge do? It sort of tries to induce a positive charge on the neighboring molecule. And the moment you have a delta plus and a delta minus between the adjacent molecules, there is now an interaction, and the interaction, of course, the nature of interaction is attractive interaction. It is important to note that this, so what is the genesis of this interaction? It is an induced dipole interaction. Important to note that the first induction is due to localization of the electron cloud or non-uniform distribution of the electron cloud around the nucleus, and the second induction is charge induced by this delta minus on the neighboring molecule. So, since what is going to be the net interaction between the two? Of course, you have a delta plus and a delta minus, and the net interaction is going to be attractive. One can, so this is what is known as the induced dipole type interaction, and this is represented by some sort of a correlation b r to the power minus 6. Of course, many of you probably have seen this type of a curve. So, this is r, the separation distance, and this is the strength. So, negative is attractive. So, it is in this regime it is attractive. What does it mean? That if the two molecules are far away, there is no interaction. In fact, this coincides, this is equal to v equal to 0, but if they come closer, then this charge induction takes place and there is a net attraction. Of course, if they now physically come closer to each other, which actually does not happen. Why it does not happen? The molecules actually do not move because of this van der Waals interaction, because by the time the second molecule sort of realizes that there is a net attraction, the location of this localized charge in the first molecule changes, because it is a very high frequency oscillation. This is not a permanent dipole, and that is also the that is a very important aspect, that this interaction takes place in all types of molecule, irrespective of whether they are polar or non-polar, independent of whether any dipole is present or not, and therefore, it is absolutely universal. Of course, if these two molecules now physically come closer, we do a thought experiment and they come closer, then what is going to happen? Their electronic orbitals, or the outer orbitals of the electrons, are going to sort of overlap, and that is going to give rise to a strong repulsion between the two. So, that in fact represents this part of the curve, and it is a shorter range electrostatic repulsion. So, that is represented by a r to the power 12 sort of expression. So, this is called the Lennard-Jones potential, or the LJ potential. This is also called the 612 potential. Now, we all knew from our school days that van der Waals force is one of the most fundamental form of forces, but in the macroscopic world we rarely see its signature. And what I mean, or try to emphasize, or I will try to emphasize upon you from now onwards, that nanoscale is also different from the macro scale, not only in terms of finite size effect, but it is also a scale where the interaction or the physics are strongly governed by the presence of van der Waals forces, and that is how why it leads to some very different and extraordinary properties which are attributed to these forces. The other thing that we will also see, I will give you some examples probably in the next lecture. The other thing we will also see that certain material properties are attributed to nanostructures. There are structures with nanoscale or hundreds of nanometer dimension, which gives rise to some extraordinary properties. So, that is what we have in this particular introductory lecture for you. The next module, we will again continue with an extended discussion and on introduction of the topic, so as to impress upon you how the nanoscale is different and how some extraordinary properties are attributed to nano patterns or nanoscale features. Thank you.